Hello. So we're back now with a video actually doing an example of a rotating mass and talking about the radial forces on it. We're going to put into practice some of the things that we talked about in the last video with the free body diagram, considering it kind of just following behind our little go-kart. This time it's going to be a small little weight attached to a string. So our example here is consider a weight attached to a massless string. The 1 kilogram weight is spun on a frictionless table in a 0.5 meter radius circle. The period of the spinning weight is 0.75 seconds. What is the tension in the string? So right off the bat, we probably want to draw a picture, right? So let's just draw a circle here. And I want to, from my center point, draw a line out, right? So this is, and it's kind of important to show this, it is a top-down view of this entire thing. This is a top-down view. And we have our little weight here. Our weight is 1 kilogram. Might as well write that. Kilogram. We know that this radius here is equal to 0.5 meters. And then finally we know that our period of rotation, 0.75 seconds. So it's kind of up to us how we want to have this rotate. I kind of generally like to have things rotate counterclockwise. Generally speaking, we're going to adopt the convention that counterclockwise is positive rotation, clockwise is negative rotation. And the only reason for that is well, not the only. I'm not going to get into that right now. Anywho, sorry. Went on a quick tangent there. But we do have our, speaking of tangential velocity, which we don't know. We're not actually given that. So let's try and draw a free body diagram now. Let's see if I can actually get the letters correct. Free body diagram. Free body diagram, we said, is as if there is a little camera just kind of following this thing as it goes around our circle. And so it's a stationary view from behind it. So we can even kind of put this as an addendum behind our thing. Let's zoom in just a little bit more. If I think about my free body diagram of this thing, obviously I have some gravity, but our gravity is actually pointing into the page according to our top version here. Right? From behind, it goes down, just straight down like normal, mg. Of course, I have the frictionless table providing some normal force up. And then because I'm going counterclockwise, radially in is to my left, radially outward is to my right. And so my tension is always going to be pointing to the left, radially inward. So I have two directions here that I can kind of sum up. I can sum up the forces in the z direction, and I can sum up the forces in the r direction. In the z direction, I have two forces. I have the normal force from our frictionless table, and I have weight pointing down. Now, the question we need to ask ourselves is this spinning mass rising off the table, accelerating off the table, or burrowing into the table? And I think not. I think it's 0 for our net acceleration in the z direction. In the r direction, though, we only have one force, tension. Right? So tension is the force that is going to give us our centripetal acceleration. So maybe I should have, I like the way that I've kind of drawn this out. I'm going to say centripetal acceleration here. I'm not going to say radial acceleration per se, because our radial forces are always going to give us our centripetal acceleration. And we know from last time that we can also write that as something else. I can write that, I don't know, let's say mv squared over r, right? Where v squared over r is our centripetal acceleration. So in this case, and I want to stress this point, there's no such thing as a centripetal force. All right. What we're saying, though, is that a force, any force, could be providing the necessary centripetal acceleration to keep things in a circle. So the force that provides that is not really special by any means inherently. There's no such thing as a specific centripetal force, right? It's really just what forces are giving this centripetal acceleration, right? I guess to really drive the point home, there's no new force that we're really defining or exploring here. Tension's old news, right? So let's keep going though. We want to know, just zoom out to our question here, what is the tension in the string? So we can kind of go through this a little bit more. T equals our mv squared over r now. What's v? Right? What is our v here? From a previous, I think we talked about this in the review of rotational quantities. We have v equals 2 pi r over my period. So if I throw that in there, right, if I substitute this 2 pi r over t in for v squared, now this gets tricky. This is tension, by the by. This is period. Oof. All right. So maybe what I'll do is say tension. Tennessee. Tension equals, now I'm going to say what? I'm going to say 4 pi squared m times, now I get this r squared divided by r, so it's just going to be r on top, over my period squared. I'll leave that as t for right now. And if I start to plug in some numbers, I get 4 pi squared times 1 kilogram, quantity squared, times my radius, 0.5 meters. Oh, sorry, my mass is not squared. Let's just get rid of that. It's just 1 kilogram. I mean, 1 squared is still 1, but we want to get the units right on this too. 0.5 meters. That's not squared because we had a r in the denominator and an r squared in the numerator, over my period, 0.75 seconds squared. And if we plug that into a calculator, 4 times pi squared times 1 times 0.5 divided by 0.75 divided by 0.75 gives me 35.09 newtons. Now, an older version of my notes, which was still online as of Sunday, had a slightly wrong answer for this value. I didn't actually square the period, but there should be an updated version of my notes online at this point. So, our tension force is providing the centripetal acceleration, and by knowing something about the period, we were able to say how fast we were actually going, and we can actually calculate that. We want to know how fast we're going. We could always calculate 2 pi r over period, right? 2 times pi times 0.5 divided by 0.75 gives me a speed of 4.19 meters per second. Knowing something about the speed, I can now figure out how much tension is in the string required to actually keep me rotating at that speed and in this circle. So that is a quick example of talking about free body diagrams of rotating objects. If you have any questions with this one, please, of course, swing into an office hour online or shoot me an email. I'm happy to answer any questions. All right. See you next time.